Unit 8.6, Trigonometry, Unit Circle. In today's lesson, we're going to apply special right triangles that you learned about in geometry to the unit circle in trigonometry. So to start off, let's look at this example. We have a 45, 45, 90 special right triangle with one of the legs equal to 3. Therefore, we know that the other leg is 3. And if we forgot what the relationship was, what the ratio was, you can use the Pythagorean theorem. And I went ahead and just used tangent of 45 to solve for 3. That's another way you could have done it. And here we have a squared plus b squared equals c squared. If we use 3 and 3 for the legs, we end up with square root of 18 equals c squared. Square root both sides, and c equals 3 radical 2. So as you can see, in a 45, 45, 90 triangle, the relationship is always whatever one leg is the same as the other leg, and the hypotenuse is that leg times a factor of radical 2. Now in geometry, you learned about another type of special right triangle, and this one is the 30, 60, 90 right triangle. So when you know what the shorter leg is, the other leg is basically a factor of radical 3. So it's whatever the shorter leg is x, here's 3, it's x radical 3, or in this case, it would be 3 radical 3. Now the hypotenuse, right, the side that's across from the 90-degree angle, is always twice that of the shorter leg. So 2 times 3 is 6. And here's another example of 45, 45, 90. As you can see, it's short. The leg is 4, right? It's an isosceles triangle, so it's 4, 4, 4 radical 2. Now in this 30, 60, 90 triangle, it's a little trickier because they give us the longer leg. And normally, whatever this is, we have to multiply by radical 3 to get this. But this time we're actually going the other direction, so we need to divide by radical 3. So in here would really be 4 divided by radical 3. Now if you remember, I didn't put this in the box yet because this is not in simplest radical form because we have a radical in the denominator. So in order to rationalize the denominator, you have to multiply the radical times itself. And this results in 4 times radical 3 over 3. And then when you double this to get the hypotenuse, you end up with 8 radical 3 over 3. Now let's take a close look at a 45, 45, 90 triangle when they give us the hypotenuse of 1. And there's a reason why this is one that we really have to pay attention to, because the 1 is, for a unit circle, the hypotenuse is always the radius. So this will be very important. So basically, to go backwards from the hypotenuse to the legs of a 45, 45, 90, you have to divide by radical 2. So divide by square root of 2, divide by square root of 2. And once again, we have to rationalize the denominator. So the legs end up being square root of 2 over 2, square root of 2 over 2. All right, these are very important. I'll highlight them. Now when we look at a 30, 60, 90 triangle with the hypotenuse given as 1, and we need to find the other legs, we basically need to just work backwards. So we know that the side across from the 30-degree angle is half that of the hypotenuse. So it's half of 1, it's 1/2. We'll leave it in fraction form. And we know to go from the shorter leg to the longer leg, we have to multiply by a factor of radical 3. So it's 1/2 times radical 3, or better written, radical 3 over 2. Just like that. Okay, so I'm going to highlight these. These are also very important. Okay, so all of that was just a review of the special right triangles that you learned about in geometry. So here in trigonometry, how do these special right triangles apply to the unit circle? Let's take a look at this example. We want to sketch the 45, 135, 225, and 315 degrees and find the xy coordinates of each point where the terminal side of each angle intersects the unit circle. So let's start with 45 degrees. So there we go. We want to find this ordered pair. Now if you remember, the right triangle makes that happen, because whatever this value is and this value is the x and the y coordinate. So we know that this is a 45-degree angle, this is a 45-degree angle, and we know that the radius is 1. In other words, the hypotenuse is 1. Fortunately, we already did the work. We see that with the 45, 45, 90 triangle with the radius with a hypotenuse of 1, square root of 2 over 2 are the legs. So we know that if this is square root of 2 over 2, and this is square root of 2 over 2, then we know that the x and the y coordinates are the same, radical 2 over 2. And this is true because we know that this is really the x coordinate, this is really the y coordinate, right? This is cosine of 45 degrees, and this is sine of 45 degrees. And this is very, very important, because as you use this to sketch out all your other degrees, 135, 225, and 315, you end up with this shape. And notice that it's the same ordered pair, the same coordinates over and over, except that you have to adjust for the signage according to the quadrant. So the x value is negative here. In quadrant 3, they're both negative, and in quadrant 4, only the y value is negative. And here, it's an interesting shape. It's easy to memorize this because it looks like a bow tie. So this is our regular bow tie because it's 45 degrees. Now here we need to sketch 30 degrees. So 30 degrees is going to be about a third of the way through. That's 30. Drop this down, that's 90, this is 60. So now we have a 30, 60, 90 triangle. Once again, we have to find out what this ordered pair is. So if we found out this length and this length, this was x and this is y. Fortunately, we already figured this out over here. So the shorter leg is 1/2 and the longer leg is square root of 3 over 2. So this is radical 3 over 2. This is 1/2, and therefore we can just plug these directly in here. X is radical 3 over 2, and y is 1/2. And now our bow tie just got skinnier. So this would be, we'll call it the narrower bow tie. Called the longer bow tie. Okay? And the same thing, the ordered pairs are all exactly the same except for the signs. Right? The signs have to be consistent with what quadrant we're in. Okay, last unit circle. Now we're going to sketch 60 degrees. And 60 degrees is right about there. Actually, that's a little too high, but right about like that. Okay, so let's go ahead and drop this down to make our right triangle, and we know this is 60. This is not 30 degrees, and this is 90 degrees. So those are 30, 60, 90 triangle. And to find our ordered pairs, we're basically going to use the same relationships we used for this previous one, except it's a different orientation because this is 60 degrees. So we know that if the hypotenuse or the radius is 1, then this length is 1/2, and this length is radical 3 over 2. So the x value goes here, and the y value goes here. Okay? Now one thing I want to show you is that if you ever forget which one is which, you can do a calculator check. So we know that 1/2 is 0.5. Now square root of 3 over 2, So here's my calculator, and square root of 3 over 2, notice the parentheses have to be closed before you divide by 2, is about 0.87. And this is useful knowledge because if I know that 1/2 is 0.5 and the square root of 3 over 2 is 0.87, then I know that radical 3 over 2 has to be the longer leg because 0.87 is greater than 0.5. So that's a good way to remember which one goes where in case you forget. So as you can see, here it is. And this bow tie is taller. This is the taller bow tie. And all of these are 1/2 and square root of 3 over 2. Once again, adjusting for all the signs according to the quadrant. Okay, let's look at Sage and Scribe number 1. Here, let's go ahead and sketch 120 degrees. So this is 90. I need 30 more to get 120. Okay, so there it is. Let's go ahead and drop this down here. And we know that the reference angle right here, this is 60 degrees. 30 degrees, 90. So once again, we're looking at a 30, 60, 90 triangle. Now, since we want to find the value, the exact value of cosine of 120, we want to determine the x-coordinate because the x-coordinate, remember, it's cosine of theta is the x-coordinate and sine of theta is the y-coordinate. So here, if you remember, the x-coordinate is 1/2. And as a matter of fact, it's -1/2 because we're in quadrant 2. And therefore, we have this as our exact value. And as you can see, you can do a calculator check. Cosine of 120 is -1/2. Sage and Scribe number 2, let's find the exact value of sine of 225. Now we know that this is 180, and another 45 degrees would give us 225. So once again, we need to find what the ordered pair is because the y value will be sine of 225. Okay, it's a 45, 45, 90 triangle, so I know it's negative radical 2 over 2. And here's our calculator check. Sine of 225 is -0.707. And if we went ahead and we plugged in negative radical 2, whoops, this didn't work, negative radical 2 divided by 2, we get the exact same answer. Sage and Scribe 3, we're in quadrant 1 because we want simply 45 degrees, and the cosine of 45 degrees would be the x value over here, which is just square root of 2 over 2. And here's our calculator check. As you can see, cosine of 45 is 0.707, and square root of 2 over 2 is also 0.707. All right, last one, we have sine of 330 degrees. If this is 90, 180, 270, 330 would be right here. You can also say 330 is 30 less than 360. So here, our reference angle would be 30, this would be our 90, and this would be our 60. So once again, we're using our coordinates and our special right triangle to find that sine of 330 degrees is simply the y value, which is -1/2. Let's do our calculator check. And as you can see, sine of 330 degrees is -0.5, which is -1/2. Good luck to you.